Right, let's move on with a few more theorems. 1, 2, there's the famous one, of course, Lagrange's. 2, 3, 4. I ran out of board, there's another one as well, 52. Okay, before I do, I promised you I would, in an earlier session, I promised I would show you the textbooks of higher level courses in group theory. Now this is junior senior level, undergrad, and group theory is just so important to mathicists, mathematical physics people who are equally at home speaking pure math as they are mathematical physics. So group theory is just so important to modern physics and to math, of course, that I thought it would be a good idea to give you, if you're going to go high level, to have a really thorough basis in understanding principles of pure mathematics, group theory, finite group theory. So you've seen the current textbook we're using many times if you've been following these lectures carefully. My book is falling to pieces. There's the undergrad text. First author is Barnard. Okay, so and I have 3 more texts here for 3 more levels at least. The M1, that's first year master's level, by Humphreys, and it's called A Course in Group Theory. And in M1 level, we will look into the structure of groups. When the order of your group is quite large and has many factors and sub-factors and sub-sub-factors and so on, there's all kinds of beautiful theorems you can create about the structure of groups, which leads in later to analysing simple groups, and consider that one of the major attractions and achievements of group theory. Now at M2 level, second year master's level, the text I'll be using, very probably, is by Kurzweil, Hans Kurzweil, and you can see that. So the theory of finite groups. Now Kurzweil also says in the introduction to his book that he too is absolutely fascinated by simple groups, especially the wonderful theorem, the classification of all possible simple groups. And one of his main aims in this text is to provide a lot of the theorems, a lot of the knowledge as prerequisite to understanding that classification and the simple groups. Now at PhD 1 level, I've chosen this one, just called simply Finite Group Theory, and the author is Aschbacher. Now Aschbacher is famous in circles of simple groups because he was one of the dominant players. It's largely due to him and a handful of others who really broke the back of the problem of classifying the simple groups. So by the time you've got these 4, so Barnard, Humphreys, Kurzweil, and Aschbacher. So once you've got these 3 graduate level texts under your belt, you'll be in a very strong position then to understand far better the nature of the simple groups and their classification. Now, I'm not quite sure yet what I'll be doing at PhD 2 level in finite group theory. I've yet to think about it. There's a lot to think about because I think I mentioned once before that that classification proof was enormous. It involved I think about 15,000, if I remember correctly, about 15,000 pages of journal proofs and several hundred mathematicians, research mathematicians working on it. And so now there's a group working now to try to simplify the proof, try and whittle it down to about 5,000 pages so they can publish it in a number of books that would sit on one shelf. And I have two of them here, and I have two others in electronic form, and I see by looking at Amazon.com, six are out, published so far, and there are more to come. So I'm not quite sure what I'll do at PhD 2 level. Also, I'll be trying to tie in string theory, at PhD level, and simple groups as well, because those two are intimately linked, and that's one of the sources of the fascination I have, and a lot of other people have, with simple groups, is their intimate link with the real world, the physical world, with physics, with mathematical physics. All right, well, that's a bit of a sideline, just throwing it in for passion's sake. All right, so let's do the first theorem. Now, actually, this theorem is critical to the big one of Lagrange's theorem, because as I was saying just at the end of the previous session, any group is in fact the disjoint union of left cosets. Right? And by disjoint meaning, if you have two sets, they are disjoint if they have no members in common. Right? Each member is, and by the definition of a set, if you have any repeats of an element in the set, you throw out the repeat. So each element in a set is distinct. Okay, so that means if two sets are disjoint, then the union of those two sets, they will all be different. Okay. All right. So how to prove this? And this is critical for the next one. So you need to understand this. So how can we show that by unionizing, just the union of sets, set union, by unionizing left cosets, we can get the whole group. That's what we're trying to show. And this union, the cosets that you union are disjoint. They have no common members, right? Well, take any element of your group. Now, since the unit element belongs to your subgroup, that's true of any group, right? So if E belongs to H, then XE belongs to XH, right? It stands to reason, right? But XE is just X, so that means that for any element X, it belongs to its corresponding coset. So X belongs to XH. Okay? That's true in general, right? Now, here's your group, right? I've just written out all the members of your group. So let's say n of them. So let's say the order of this thing is big N. So there's every member of your group, right? Now, you can rewrite this set as a union of sets, and the set has one element each. So that E would correspond to this set. That element corresponds to that set of one element. That element corresponds to this set of one element. This corresponds to that, and so on. All right? So you can rewrite that as this. Now, if you do the union of all these, you just get this, right? So I'm just going the other way from here to here. Now look, for each element here, that belongs to your coset. So this and this is equivalent. Maybe that's not so obvious, but give it a little thought. Right? Since this element belongs to its corresponding coset, X belongs to XH, right? So this is a set, and this is a set. Now there are more elements in this than this, of course, but if I get any repeats, it doesn't matter, right? You just throw them out. You throw out the repeats because we're making a set. So if you give it a bit of thought, you'll see that and that are the same, all right? And what is this? Well, look, it's a union of cosets, right? Coset, I've underlined that, coset. So G here is a union of cosets, right? Now it says here G is a union, disjoint union. So we need to show that they're disjoint. So either Now remember, you can have cosets that are the same for different elements. So we need to show now, so if I take any two of these cosets, let's say xih or xjh, I take any two, I now need to show that either they're the same, so the same cosets, so the same set, or they're disjoint, they have no element in common. It's one or the other. And if I can show that, then this union of cosets, each coset will be different from the others. So I'll then have a union of disjoint cosets. So I need to take, so I'll take any two, so xih, xjh, and I'll need to show that either this is equal to that, or they have no elements in common. They're disjoint. Right? So that's what I now need to prove. All right. Well, let's assume that there is an element in this set that's also in this set. Okay. So in other words, these two are not disjoint. So that means I need to show either they're the same element, or they're not. Right? Okay, so if this is true, if these two sets are equal, there will be, well, put it this way, if there's a